Welcome, focused learners, to today's exam strategy session. I like to call this one the film director approach to your Cambridge Computer Science exams, specifically targeting syllabus 0478. Think about your absolute favorite blockbuster movie. It's gripping, right? Every single scene has a purpose. There's zero filler. Scene by scene, the director builds a masterpiece. Well, that is exactly how you need to approach your exam answers. Cut the filler, keep the action, and build a blockbuster response. Today, we are going to apply this exact framework to one of the most rigorously tested topics, the physical layer and network infrastructure. To help us out, I want you to imagine two typical students. First, we have Alex. Alex is brilliant, but Alex overloads every answer with raw computer science facts and provides zero analysis. Then we have Sam. Sam rushes, panics under the ticking clock, and completely misses the command word requirements. Sound familiar? Let's look at their flawed answers, grab our red pens, and transform them into top-tier, maximum mark responses. Let's get into it.
Here is the storyboard for today's blockbuster. Act 1, we tackle the physical layer foundation, identifying where students like Sam lose easy marks. Act 2, mapping the network with topologies, where we'll reveal our core exam strategy. Act 3, directing data with switching techniques, where we'll transform those red pen marks into green check marks. And finally, Act 4 and 5, sharing the medium with multiplexing, where we build our final interactive answering system. We are mapping out this complex networking topic sequentially, and by the end, you'll have a blueprint to tackle any past paper question they throw at you. Okay, Act 1, the challenge. Let's dive into our first core concept. Every great structure and every great exam answer needs a solid foundation. In computer science networking, that starts right here at the base level. Imagine an exam question asks, describe the role of the physical layer in a network model. 6 marks. The timer is ticking.
So, what is it? The physical layer is the absolute foundation of network communication. It's the lowest layer in the OSI model. Its job is to convert data frames from the data link layer into raw bits, ones and zeros over a physical medium. Now, Alex sees this question and immediately writes down everything he knows about cables. He writes a massive paragraph about copper versus fiber optics, but forgets to actually define the layer's primary role. Sam, on the other hand, just writes, it sends ones and zeros. Both of them are dropping massive marks here. You need to structure your answer. Your point is that it's the lowest layer. Your evidence is that it converts data frames. Your explanation is that it outputs raw bits. You see how we build it scene by scene? If the examiner asks you to evaluate the attributes of this layer, you can't just list these bullet points. Alex would list analog versus digital, wired versus wireless, simplex, duplex, attenuation, dispersion, and move on. Zero analysis. To get the marks, you have to explain the why. Think of these attributes as our city's zoning laws. You have to explain that transmission modes dictate whether traffic flows in one direction, like simplex, or two directions, like full duplex. You have to explain that noise handling is crucial because attenuation causes signal deterioration over long distances. Don't just give the examiner the vocabulary, give them the application.
Moving into Act 2, the strategy reveal. Now that we have our cables, let's look at how we actually arrange the buildings and streets. And as we do this, I'm going to reveal exactly how top students structure their topology answers using a specific framework.
First, the definition. Topology is essentially your network's roadmap. It details how nodes are connected physically or logically. Now, before we look at the specific topologies, we need to talk about command words. In a Cambridge exam, state means give a short answer. Describe means state the main points. But evaluate or compare, that requires the Peel framework. Point, evidence, explanation, link. Keep this framework in your head as we analyze the next few slides.
Take a look at this brilliant illustration of a bus topology, where one single backbone cable connects all computers using drop lines and taps. Now, before we apply the Peel framework to this, I need to remind you of something critical. Before we continue, subscribe to our YouTube channel, Ace the Exams, at @AceTheExams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the bus topology. If you are asked to evaluate this, what is your opening point? Let's do a 30-second mental challenge. Spot the Peel in this potential answer. Point. The bus topology is highly cost-effective for small networks. Evidence. It uses a single backbone cable to connect all nodes. Explanation. Because it requires minimal cabling compared to other setups, the initial installation costs are drastically reduced. Link. Therefore,
It is the most budget-friendly choice, though it risks a single point of failure. Boom, that is a blockbuster answer. Alex would have just said it's cheap but breaks easily. Sam would have skipped the explanation entirely. You need to link your point back to the command word. Remember, a break in that main cable brings down the entire network, and scalability is severely limited due to data collisions.
Welcome to Act 3, the transformation. We are going to take Sam and Alex's rushed, overloaded answers and turn them into gold. Here is the ring topology, where devices form a closed loop, each with a dedicated point-to-point connection to its two adjacent neighbors. Imagine an exam question asks, explain how data collision is prevented in a ring topology.
Sam writes, data goes in a circle so it doesn't crash. Red pen time? That is a 1-mark answer for a 3-mark question. Let's transform it. Let's apply our blueprint. Point: data collision is prevented through sequential traffic management. Evidence: the network utilizes a token passing system. Explanation: only the node currently holding the token is permitted to transmit data across the closed loop. Link: this sequential access ensures multiple nodes cannot transmit simultaneously, completely eliminating collisions. Look at that. We just transformed a failing answer into a perfect score. But don't forget the downside for your evaluation questions. Troubleshooting is notoriously difficult, and if one node fails, the whole loop is broken.
Here we have the star topology. All nodes connect to a central hub. This is incredibly popular in modern networks. Before we break down the exam strategy for the star topology, I need you to focus here. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at AceTheExams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @AceTheExams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, let's look at Alex's answer for the star topology. The question is, discuss the reliability of a star topology. Alex writes an entire page detailing the brand names of switches, the type of copper used in the cables, and the history of the hub. 0 marks for relevance. Let's cut the filler. Point: the star topology offers high reliability through isolated connections. Evidence: every node has its own dedicated cable to the central hub. Explanation: if one cable fails, only that specific node is disconnected, leaving the rest of the network fully operational. Link: however, the overall reliability is entirely dependent on the central hub. If the hub fails, the entire network collapses. Crisp, accurate, blockbuster.
Next up, the mesh topology. Every node connects to every other node. When examiners ask about this, they are looking for the word redundancy. A full mesh topology utilizes routing or flooding techniques, so data is almost never lost. If one path fails, the data simply takes another route. It is incredibly robust, but the sheer amount of cabling makes it exceptionally expensive and complex to maintain. Always weigh the cost against the reliability when comparing topologies.
Welcome to Act 4, the interactive workshop. I want you to look at this complex data table. This is your cheat sheet. We are doing Challenge 1, the data scan. You have 60 seconds on the exam clock to extract the core trend here. What is the relationship between cost and reliability? Look closely. As reliability goes from low in the bus to high in the star and ring to excellent in the mesh, the cost scales from cheap to expensive to very high. The core trend you need to extract for your exam is that network design is always a compromise between budget constraints and fault tolerance requirements.
All right, we've built the roads. Now, how do we efficiently direct the data traffic? Let's move on to switching techniques, a massive area where students drop marks by getting their definitions tangled up.
Time for Challenge 2, Find the Flaw. I am going to read you a sample paragraph about switching, and I want you to find the sentence that loses the marks. Listen closely. Switching is used in networks. It takes data from an ingress port and throws it out randomly. It directs signals to a hardware destination via an egress port. Did you catch it? The flaw is throws it out randomly. Switching is highly specific. It is the calculated networking practice of directing a signal from an ingress port, which means incoming, toward a particular hardware destination via an egress port, which is the exit. Examiners want precision.
This is one of the most common comparison questions in the syllabus: circuit switching versus packet switching. Let's look at the stark contrast. Circuit switching locks down a pre-established, dedicated physical path for the entire duration of the transfer. It's like reserving an entire highway just for your car. Packet switching, however, divides the message into little chunks called packets. It routes them independently, on demand, based on available resources. They might all take different paths and arrive out of order. If you get a compare question, use the Peel framework. Point out the path difference, give evidence of how they travel, explain the impact on network resources, and link it to efficiency.
Now for Challenge 3, Speed Writing. You have a 30-second visual timer in your head. The prompt is, outline the phases of virtual circuit packet switching. Go! What are you writing? You need to mimic a dedicated circuit while using packets. Phase 1, the setup phase to establish the logical connection. Phase 2, the data transfer phase, where packets travel the exact same path in order. Phase 3, the connection release phase, to free up the network resources. If you just wrote "it sends data," you're pulling a SAM. You need these exact 3 steps for full marks.
Finally, Act 5, the final system. We've routed our data, but how do we allow multiple streams of traffic to use the same exact highway simultaneously to save on infrastructure costs?
This is multiplexing. It integrates multiple analog and digital signals into a single signal transmitted over a shared high-capacity medium. It's exactly like an ultra-efficient carpool lane. This is where we finalize our computer science success blueprint. Rule number 1, command word decoding. When the question asks you to define multiplexing, this slide right here is your answer. You state exactly what the technique does. Don't drift into explaining how it works until you've defined what it is.
Now we apply Rule 2, the Peel framework application. Look at frequency division multiplexing, or FDM. Analog signals are combined by separating them into distinct bandwidth channels, like tuning into different radio stations. So if asked to explain FDM, your point is that it separates signals. Your evidence is that it uses distinct frequency bands. Your explanation is that this prevents interference between modulated analog signals. And your link is that it allows simultaneous transmission over one medium.
Wavelength division multiplexing takes this same concept but applies it to the incredible data rates of fiber optic cables, splitting and combining different light wavelengths. And this brings us to Rule 3, the time management matrix. When you see a complex diagram like this in an exam, don't panic and waste 10 minutes staring at it. Scan for the keywords, light sources, fiber optics, combining wavelengths. Allocate your time based on the marks available. A 2-mark question on WDM should take you maximum 2 to 3 minutes to write. Keep the action moving.
And for digital data, time division multiplexing rotates through signals in synchronized time slots, ensuring everyone gets a fast, organized turn to transmit. Listen closely, because this is where the strategy really pays off. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now at acetheexams_IGCE and click that bell. Don't let another exam pass you by.
To truly master this topic, here is your final challenge. Combine everything we've built in our digital city. If you need absolute resilience, no single points of failure, what do you use? You use a mesh topology combined with dynamic packet switching, so data can always find a new route. Understanding that synergy is your ultimate blockbuster conclusion. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.